Hello, hi, good afternoon, good afternoon, good afternoon. Hello everyone, good afternoon, how are you all? Good afternoon. Am I audible guys? सर आए हैं आ गए बिल्कुल एकदम आ गए आप आप सब लोग भी आ गए हो हाँ ओके सो वेलकम बैक टू गेट वाला एंड गाइस just give me a sec, just let me arrange my screen. Okay, so guys, welcome to Gatewala, and guys, today we are going to do questions which are going to be the most expected question that we can see this year for Gate 2026 in applications of thermodynamics. So I hope guys, yesterday you might have done the revision of applications of thermodynamics. Today in the afternoon we are going to do the questions of ATD. And in ATD, we have three topics, that is refrigeration and air conditioning, internal combustion engine, and power plant engineering. So we will be doing all the questions related to these topics. And I feel those questions which I have brought over here, they are the question of gate standard. That means you can expect the questions like that only in the gate. And for every question, guys, I would request you all that you attempt those questions very seriously. You try to take as low as time possible, though I'll be giving you roughly around 2 to 3 minutes of time, because for every question you have in gate, for every let's say question, you have around 2 to 3 minutes. So you should attempt those questions, attempt these questions within that time frame only. Okay, guys, also I hope you all know that there are Maharevisions and Mahabhyas are going on. So today you have Maharevision of fluid mechanics at 4 p.m. Shivam sir will be taking, and this is the schedule of Maharevision. I hope everybody is following religiously, and also Super 20 and Mahabhyas. So today in the evening we have at Gatewala Mechanical Channel also Mahabhyas. There also we will be doing some more questions. So most probably 20 question we will be doing over here, and there we will be doing more question. So guys, are you ready? Is everyone ready with the calculator and your rough notebook and all? So should we start the questions? Okay, so guys, let's start the questions one by one, and your time starts now. So first question is on reversed Brayton cycle. Quickly solve the question and try to get me the answer. Which one is correct? It says a reversed Carnot refrigerator operates between two thermal reservoirs at -5 and 35 degrees centigrade. If the refrigerator removes 1.2 kilowatt of heat from the low temperature reservoir, then the minimum power input required to operate the refrigerator is. So quickly, fast, everybody do the question. Try to attempt the question and get me answer that what is the right answer. Quickly, all of you do it. And I don't want anybody to be copying it from others. Do your own question. Okay, do your own calculations and get your own answer. Okay, chalo. So the question is on reversed Carnot refrigerator system. Very good, very good. You guys have already started giving answers. Excellent. Excelanto. Very good, very good. C, 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 C. Anybody who is not C? Is there any other option than C? Have all of you got C? So I see that only 6 students have got C. How about remaining student? Only 10% of the student have given me answer. What about the remaining 90%? Guys, what is happening? Okay. So what is the answer? So guys, see, this is a reversed Carnot cycle, and for reversed Carnot cycle, we know that the COP of refrigerator, the COP of refrigerator is defined as COP of refrigerator. Since this is a refrigerator, so low temperature divided by T high minus T low. And we know that this temperature has to be written in kelvins. Otherwise, your answer will be wrong. So T low minus 5 degrees centigrade is 268 Kelvin divided by 35 degrees centigrade. 35 degrees centigrade is 308 minus 268. So from here you can do 268 divided by 40. So this you will get 6.7. So the COP of refrigerator is 6.7. Now once you have calculated COP, now you can calculate power. So you know that COP is defined as, COP of refrigerator is defined as refrigeration effect divided by power. So you have to calculate power. So power will be equal to refrigeration effect divided by COP. Refrigeration effect, it is saying 1.2 kilowatt. So 1.2 kilowatt divided by 6.7. This you will get as 0.18 kilowatt. Okay. So the right answer would be 0.18 kilowatt. Very good. Excellent. Everybody has done it correct. It's a very good question, and all of you have got the answer to be correct. What about others? Somebody has given me answer to be 1.7. Guys, you should not be making any mistake. Okay, question number 2. A vapor compression refrigeration system operates between an evaporator temperature of -20 and a condenser temperature of 30. The following enthalpy values are given. Enthalpy at compressor inlet 405, enthalpy at compressor outlet 455, enthalpy at condenser outlet 245. If the mass flow rate is ये क्या लिखा है भाई? सुपर कैलिफ्रेजिलिस्टिक एक्सपिलिडिशियोइश. अबे शशि थरूर के बेटे, ये एप्लीकेशन ऑफ थर्मोडायनेमिक्स की क्लास चल रही है, अंग्रेजी की क्लास नहीं हो रही है. चलो, डिटरमाइन द सीओपी ऑफ द सिस्टम. फटाफट से कैलकुलेट करो. योर टाइम स्टार्ट्स नाउ. Mass flow rate of refrigerant is 0.06 kg per second. What is the right answer? क्या आंसर आ रहा है? ओके. गौरव, अनुभव, आदित्य, अर्पित, आर्यन, आकाश. क्या बात है भाई, ए वाले ही नाम है क्या सारे? आजकल हर कोई मम्मी पापा अपने बच्चों का नाम ए से ही लिख रहा है क्या? ए के अलावा कोई नाम है या नहीं है आजकल? चलो, वेरी गुड, एक्सीलेंट. सो द राइट आंसर इज 3.2. गाइस, आपको देके रखा हुआ है वेपर कंप्रेशन रेफ्रिजरेशन साइकिल, और इसमें एंथैल्पीज उसने देके रखी हुए. ठीक है. सो इट इज 1, 2, 3 एंड 4. तो उसने कहा है एट 1 एंथैल्पी H1 इज 405 किलो जूल पर केजी, H2 is 455 kilojoule per kg, and H3, it is the condenser exit is 245. 245. So 245 kilojoule per kg. So from here you can calculate refrigeration effect, that is H1 minus H4. That can be written as H1 minus H3. That is 405 minus 245. That is 160 kilojoule per kg. Okay. So refrigeration effect आपका मिल जाएगा 160 kilojoule per kg. And then the power consumed, which is the work of compressor. So work of compressor will be equal to 455 minus 405. That is 50 kilojoule per kg. So work आ गया refrigeration effect आ गया. So you can calculate COP. COP will be equal to refrigeration effect, that is 160 divided by 50. So that is 3.2. So COP will be 3.2. Very good, excellent. Everybody has given same. मार्केट में नाम की कमी होगी, मार्केट में नाम की कमी हो गई, या लड़कियां बोल रही हैं कि हमें सिर्फ ए नाम के लड़के से ही शादी करनी है, जिसका नाम ए से शुरू होता है, मैं तो उसी की दुल्हनिया बनूंगी, इसलिए सबने ए से रखना शुरू कर दिया है. लाइन में सबसे आगे खड़ी होंगी. ओके, चलो नेक्स्ट. An air refrigeration system, Bell-Coleman cycle, operate between the following states. Air enters the compressor at 1 bar. Oh, sorry. I was supposed to be speaking in English. I'm so sorry. You guys are making me speak in Hindi, eh? So, air enters the compressor at 1 bar and 280 Kelvin. Air is compressed isentropically to 5 bar. After cooling at constant pressure, the air temperature becomes 300 Kelvin before entering the turbine. So air then expands isentropically in the turbine back to 1 bar. Assuming air behaves as an ideal gas with G, this is not G, this is gamma. With gamma 1.4 and Cp 1.005, determine the refrigeration effect per kg of air in kilojoule per kg. Quickly, you have got 2 minutes to solve this question. You have to calculate what is the refrigeration effect per kg. So what is the right answer? This is a very good question, guys. It should not take more than 2 minutes. If it is taking more than 2 minutes, that means you guys have not understood the question at all. Okay. So Aryan has given, Divya has given, Anubhav. Okay, very good. How about others? So we have got 3 answer, 4 answer, all are wrong. All are wrong answers, eh? Okay, 91. 91, everybody is getting 91. Sure, everybody is getting 91 and 91 is the right answer. Does everybody think this is the right answer? 91.03. Okay. So what is Bell-Coleman cycle? Bell-Coleman cycle is the reversed Brayton cycle. So guys, it is telling you that in a reversed Brayton cycle, so first let's draw the diagram. So guys, I am just giving you the diagram for understanding purpose only. In exam, you don't have to draw the diagram. You have to put everything in your mind. So you have to solve everything over here in your mind. So the moment it says Bell-Coleman cycle, that means you should have this picture in mind. So this pressure is 1 bar and this pressure is 5 bar. It is saying the air over here is at 280 Kelvin. It is compressed isentropically to 5 bar. And after that, it is cooled and the temperature over here is 300 Kelvin. Now he is asking you what is the refrigeration effect. So when you want to write refrigeration effect, you know that refrigeration effect is equal to, if this is location 1 and this is location 4, then it is H1 minus H4. That is equal to Cp into T1 minus T4. He has already given you T1, which is 280 Kelvin. So you have to calculate T4. So to calculate T4, what you have to do, you know that this temperature is given as 300 Kelvin. So you have to calculate this. Pressure ratio is also given. So you can use the relation T3 by T4 is equal to P3 by P4 ki power gamma minus 1 over gamma. And from here you can calculate T4. So guys, you don't have to calculate T2. Lot of you might have calculated T2, but that is not required over here. Okay. So from here you can calculate T4. So T4 will be equal to 300 divided by 5 to the power 0.4 divided by 1.4. You can do this calculation directly and you will get the answer to be 189 Kelvin. Now once you have got 189 Kelvin, now you can calculate refrigeration effect, that is 1.005 multiplied by 280 minus 189. Exact, it will come out to be 91.03 kilojoule per kg. So that is the right answer. Everybody has given it correct, but the calculation has to be very fast. It should have taken only 1 minute. Okay, your calculation should have started from here only, and then there should have been 3 steps. Most of you took more than 2 minutes, so that is not justified. Is it clear? Anyways, the more important thing is you have to do the answer correct. Okay, and everybody has got the answer correct, so I am happy about that. Chalo, next. Next question is on psychrometry. So your time starts now. Let's see who gives me the answer first. So moist air at 1 atmospheric pressure is at 30 degrees centigrade. The partial pressure of water vapor in air is 2.5. Saturation pressure at 30 degrees centigrade is 4.25. Specific humidity you have to calculate, and relative humidity. You have to calculate specific and relative humidity. Quickly, let's see who does it correct. A, moist air. What are you not getting in moist air? Akash. Should I write dry air over here? Should I write dry air? Huh? So what is the right answer? A is the right answer. So guys, it is given that PV is equal to 2.5 and PVS is given as 4.25 kPa and kPa. So relative humidity, you can directly calculate. Relative humidity is defined as PV divided by PVS. So 2.5 divided by 4.25. This you will get 0.588. roughly 0.9. Sir, what is moist air? I am asking. My goodness. You are asking what is moist air? Air which is gilly. Okay. And omega. Omega is 0.622 into PV divided by PT minus PV. So 0.622 multiplied by PV is 2.5 divided by PT. PT is given as 1 atmosphere. So here it is given as 1 atmosphere and this is kPa. So you have to convert this 1 atmosphere into kPa. So 101.325 minus 2.5. When you will do this, you will get omega to be 0.0158, I think. Okay. 0.0158 kg per kg dry air. So the right answer is 0.016 and 5.59. Understood? Okay. Very good. Let's do another question. Iron Man, why are you laughing? You are laughing on Gilly. Okay. Air at 30 degrees centigrade enters a cooling coil. The coil can fully cool the air to 18 degrees centigrade. But the actual exit air temperature is measured at 22 degrees centigrade. The bypass factor of cooling coil is. What is the bypass factor of cooling coil? Quickly, all of you. Oh my God. I am getting so many answers. Very good. Guys, it is written round of 2 decimal places. I hope everybody understands what do you mean by 2 decimal places. 0.66667. Is this 2? 0.3. Is this 2? 0.3333. Which one is 2? Huh? Ah, oh my God. I am got Arpita have got 1.166. Excelanto. Amazing. Huh? Amazing, amazing. Seriously, guys? Seriously, 0.67. Guys, bypass factor is nothing but it is the inefficiency of coil. It is not the efficiency of coil. It is inefficiency of coil. That means how much temperature the coil has not been able to achieve. So there is a coil which was supposed to cool down the air to the temperatures of 18 degrees centigrade. But when the air is going out, it is going out at 22 degrees centigrade and it is entering at 30 degrees centigrade. So bypass factor is defined as how much temperature drop that has not been achieved. So this is the temperature drop which has not been achieved. So 22 minus 18 divided by what was that possible? So 30 minus 18. Okay, so this is 4 divided by 12, that is 1 divided by 3, that is 0.33. 0.33. Guys, I hope you understand that 0.3333 is rounded off to 0.33, not 0.34. This is wrong. Okay, and those of you who are getting 0.67, 0.67 is the efficiency, not the bypass factor. Okay, this is very easy question, yaar. How can you make this wrong? Chalo, next question. An air standard diesel cycle has a compression ratio of 16 and a cutoff ratio of 2. The specific heat ratio is 1.4. If heat added during the cycle is 500 kilojoule per kg, calculate the thermal efficiency of cycle. Quickly calculate it. What is the answer? Okay, very good. Okay. Okay. So guys, what is the efficiency of diesel cycle? Efficiency of diesel cycle is written as 1 minus 1 over r ki power gamma minus 1. Okay, this is the efficiency of Otto cycle. Then you have to draw like this. Alpha ki power gamma minus 1 divided by gamma into alpha minus 1. Okay. So now you can put in the numbers. So 1 minus 1 divided by 16 ki power 0.4 divided by 2 ki power 1.4 minus 1 divided by 1.4 into 2 minus 1. When you will solve this, if you are not making any mistake, then you will get 0.61. And if you are making mistake, then you will get something else. So I had given you the choices to be very close by, so that you, if you make any mistake, your answer would be lying somewhere at a different location. Okay. So this was very easy. Everybody has got it correct. Very good. Okay. So I see 30 to 40% of you are giving answers. 30 to 40% of students are giving answers. What about others here? 60, 70%. Most of you are not even giving the answer, even if it is wrong. Guys, make a mistake over here. Try to attempt the questions. Okay? And don't tell me that you don't have calculators. Chalo, next question. Next question on specific fuel consumption. An engine develops a power of 50 kilowatt. The fuel consumption rate is 15 kg per hour. The brake specific fuel consumption is. Very easy question. Very straightforward. What will be the brake specific fuel consumption? Quickly. What is the right answer? Okay. So we know that what is brake specific fuel consumption? Brake specific fuel consumption is defined as mass flow rate of fuel multiplied by 3600 divided by brake power. Okay. So now brake power has to be in kilowatt and m dot f should be in kg per second. So I was expecting somebody to make a mistake, and Abhi Roshan has done my name Roshan. Okay. So m dot f should be in kg per second. So 15 divided by 3600. Okay. Multiplied by 3600 divided by brake power is 50. So the answer would be 15 divided by 50, that is 0.3 kg per kilowatt hour. If you remember, I had told you yesterday while doing the Maha revision that your value should come what somewhere between 0.2 to 0.3. This is what is the general range of specific fuel consumption. If your answer is something different, then you should be making mistake. Chalo, next. A petrol engine consumes fuel at a rate of 0.6 kg per minute. The calorific value of fuel is 44,000 kilojoule per kg. The engine develops 60 kilowatt brake power. What is the thermal efficiency of engine? So quickly calculate what is the thermal efficiency of engine. Quickly calculate. What is the answer? 14%. D. C or D? 22%. $13.63. Array options are given in front of you. You don't have to write 13.6. Options are given. It is a multiple choice question. What is the right answer? Okay. So it is given that a petrol engine consumes fuel at a rate of 0.6 kg per minute. That means mass flow rate of fuel will be equal to 0.6 divided by 60 kg per second. Okay, so this is mass flow rate of fuel. Now calorific value is given as 44,000 kilojoule per kg. So from here you can calculate what is the amount of heat released which will be supplied, that is mass flow rate of fuel multiplied by calorific value, that is 0.6 divided by 60 into 44,000. Okay, so now you can solve this. So 0.6 divided by 6 will be 10 and 10, this will be 440. So the energy that is supplied is kilojoule per second or kilowatt, 440 kilowatt. And what is the power developed? Power developed is given as 60 kilowatt. So efficiency will be equal to power developed divided by the heat supplied. Okay, so 60 divided by 440, it will come out to be roughly 14%. ठीक है, 13.8. Okay, very good, excellent. So I am very happy that everybody is giving me right answers. Very good, guys. I am enjoying it. That means you guys have prepared applications of thermodynamics well. Okay, and you must be getting out of whatever the mark 6, 7, 5 that question comes. For an ideal Brayton cycle with fixed maximum and minimum temperatures, which one of the following statement is or are correct? Why this is multiple choice? This should be multiple selection question. Yes. Okay, so question is multiple selection question. Which of the following is or are correct? So with the temperature, maximum and minimum temperatures fixed in an ideal Brayton cycle, which of the following is or are correct? Sir, that means 87% energy is being wasted. Yes. I hope that is what an efficiency means. If efficiency is 14%, that means 86% energy is getting wasted. That's correct. This is what is the scenario which is correct for most of the bikes. Nowadays, if you see the bikes which are 350cc bikes, the efficiency of these bikes is very low. 20, 25%, 20%. ACD, AD, CD, AC, my God. I'm getting so many answers. A and D, A, C and D. So thermal efficiency increases with increase in pressure ratio. Network output increases indefinitely with pressure ratio. There exists an optimum pressure ratio for maximum network. Compressor work increases with pressure ratio. Very good. So wastage is used, that I know that is huge. 86% wastage is huge wastage, I know. None of the engine has efficiency more than 25% in real life. A and C. Wow, A and C. Good. So this is the one question which has tested your knowledge. So the thermal efficiency increases with increase in pressure ratio. You know that for a Brayton cycle, efficiency is 1 minus 1 over R to the power gamma minus 1 over gamma. And as your R increases, this decreases, and whole efficiency increases. We have also drawn the curve like this. So we have seen that the efficiency increases as the pressure ratio increases. So this is R equal to 1, this is R max. And at R equal to R max, efficiency is equal to Carnot. So statement A is correct. Network output increases indefinitely with pressure ratio. Network output is this. So network output does not increases indefinitely with pressure ratio. No, it increases, reaches a maximum, and then decreases and goes to 0. So the second statement is wrong. Okay. Third statement, there exists an optimum pressure ratio for maximum network output. Yes, this is correct. This is the optimum pressure ratio for maximum work. Is it clear? So this third is correct. Okay. Now let's go to the fourth question, for which most of you have been making mistake. Guys, compressor work increases with pressure ratio. What is compressor work? Work of compressor is defined as Cp into T2 minus T1. And this can be written as Cp. You can take T1 common from here. This becomes T2 by T1 minus 1. That becomes Cp into T1. What is T2 by T1? R ki power gamma minus 1 or gamma minus 1. This is work of compressor. Now if you see, everybody, if you see over here, as R increases, this quantity increases. This whole quantity increases, so work of compressor increases. It keeps on increasing. the compressor work is maximum at R equal to R max. Compressor work is maximum at R equal to R max. This statement is correct. Lot of you have made a mistake. You have given A, C or either A, D, or most of you have not written D. I hope you understood what is the problem. This increases. Those of you, Abhirosh, Shamant, okay, then Aditya. Is it clear to everyone? Chalo, very good. Next, in a Brayton cycle with regenerative, which of the following is or are correct? This should also be MCQ. Regeneration increases thermal efficiency at low pressure ratios. Regeneration reduces turbine work output. Regeneration effectiveness depend on the inlet temperatures. Regeneration is ineffective when turbine exit are lower than the compressor. MSQ hai ye bhi. This is also MSQ. Sir, can we reduce WC decrease if we take W? Oh my God, what are you doing? W net by QS is efficiency. W net by Q supplied is efficiency. So you are saying that as efficiency increases, that means W net increases. No. Efficiency is increasing because in the end, this comes in the form of 0 by 0. W net becomes 0 because turbine and compressor work both are same. Okay? Chalo. Fatafat solve this question. My God, my God. A, C, D. Regeneration increases thermal efficiency at low pressure ratios. Very good. Regeneration reduces turbine work output. Very good. Regenerator effectiveness depends on inlet temperatures. Regeneration is ineffective when turbine exit temperature is lower than compressor exit temperatures. So this is again a very good question, guys. So you have completely understood ATD, but you have not understood heat transfer. Okay. So this part is your week now. Okay. ATD you have understood, but heat transfer is not clearly understood. So the question says regeneration increases thermal efficiency at low pressures. That's correct. Why? Because we know that at low pressure ratios, the efficiency of regeneration cycle is very high. So at low pressure ratios, efficiency increases. Okay. So the option A is correct. Regeneration reduces the turbine work output. This is wrong because W turbine does not change with regeneration. Let's go to the last. Regeneration is ineffective when turbine exit temperature is lower than the compressor exit temperature. That is also correct. So in case of Brayton cycle, if you see, if your temperatures are like this is your compressor exit and this is your turbine exit. So there will not be any effective because the turbine exit temperature is, let's say, 500 Kelvin and this is 700 Kelvin. So the air that is coming out of the exhaust will be at lower temperature as compared to compressor. So if you do the heat exchange, this temperature will come down and this will go up. Okay, so this is not a justified way of applying regeneration. So this statement is also correct. So A and D both are correct. Now what happens to the regenerative effectiveness depend on the inlet temperature? Guys, does effectiveness of a regenerator depends on the temperature, inlet temperatures of the heat exchanger? In heat transfer, you might have understood. On what does the effectiveness of heat exchanger depends on? What are the parameters on which the effectiveness of heat exchanger depends? Does it depend on the inlet temperature? No. Have we ever said in Brayton cycle that regenerator has the inlet temperatures as 700 and 500 and effectiveness is 0.7? If we increase the temperature to 800, the effectiveness will change. Is it? No. So this is wrong. Right answer is A and D. Okay? Very good. Chalo, let's go to the next question. Okay, this is an Otto cycle. Quickly do it. अरे effectiveness is defined as कितना हुआ divided by कितना potential था, but does it depend on what are the inlet temperatures? Let's say this is a regenerator and you have temperature. So the temperature TCI and THI. So he's saying the effectiveness depend on THI and TCI. Does it? No. Effectiveness is defined as TC out. Let's say this is TC out. So TC out minus TC in divided by THI minus TCI. This is what is the effectiveness. And this effectiveness has these two temperatures. But does it depend on these two temperatures? No. The output will depend on these temperatures and effectiveness. The formula is like this: TC out minus TCI. This will be equal to effectiveness multiplied by THI minus TCI. This is what is the formula. So effectiveness is not depending on these two. This output is depending on effectiveness and these two inlet temperatures. Okay? Okay, so what is the right answer? So it says an air standard Otto cycle has a compression ratio of 9 and specific heat ratio as 1.4. If the heat added during the cycle is 400 kilojoule per kg, calculate the heat rejected during constant volume process. What is the heat rejected? What is the heat rejected? Okay, so everybody has got it correct. Okay, so what will be the efficiency? Efficiency of cycle is 1 minus 1 over R to the power gamma minus 1. That is 1 minus 1 over 9 to the power 0.4. And this will be equal to 0.61. So efficiency will be 61%. So if efficiency is 61%, then W net will be equal to efficiency multiplied by heat supply, that is 0.61 multiplied by 400, okay, kilojoule per kg, and heat rejected will be equal to heat supply minus W net. Okay, so you can solve this. You will get this to be 166 kilojoule. Okay, So the right answer is 166 kilojoule per kg. Everybody has given me correct answer. Those of you who want to see it in other way, you can write that if this is 0.61, then the heat that would be released would be the fraction of, oh sorry, not 61, 0.58. This was coming out to be 0.58, I suppose. Just hold on a second. Where is my history? Okay, so 0. No. 0.58, not 61. This is 0.58 and this is 0.58. Okay, yeah, that's correct, 0.58. Okay, chalo. So let's go to the next question. Next question is on the compressible flow. Which of the following statements are correct? My God, why he has written MCQ everywhere? Mach number is the ratio of flow velocity to local speed of sound. For Mach number, the flow is subsonic. This is MSQ again. Okay. So, multiple selection question. Mach number is the ratio of flow velocity to local speed of sound. Mach number less than 1, flow is subsonic. Speed of sound depend on the pressure and density independently. Mach number depends on gas temperature. So, which is the correct answer? A, B, C, D, all four are correct. A, B, D, A, B, D, A, B, D. Oh. Okay. So, my UPS has started making 2-2 sound. Light is not there at my place for last 2.5 hours. And it seems I might have to curtail the session. Don't shout, yeah. Okay. So let's solve this. So it says Mach number is the ratio of flow velocity to local speed of sound. That's correct. So Mach number is equal to velocity divided by speed of sound. Velocity divided by c. So this is correct. For Mach number less than 1, the flow is subsonic. That is correct. So Mach number less than 1, the flow is subsonic. Mach equal to 1 is sonic. Mach greater than 1 is supersonic. Okay. So that is also correct. Let's go to the third statement. Speed of sound depend on pressure and density independently. Guys, this is wrong. So speed of sound is, if you see, the speed of sound is equal to under root of gamma into R into T. So it depends only on the temperature. It does not depend on pressure and density independently. Okay, it does not depend on pressure and density. So the third statement is wrong. The Mach number depends on gas temperature. This statement is correct because Mach number is equal to velocity of the fluid flow divided by speed of sound, which is under root of gamma into R into T. Okay, so Mach number depends on the temperature T. Is it clear? So that's correct. So the right statement is A, C, and A, B, and D. C is wrong. My God, it is continuously making sound. Okay. Anyways, let's see for how long it goes. So what I will do is, you can do this question. I will switch off my light. Okay. So I hope everybody must be this question must be visible. So what I'll do is, while solving the question, I will switch on the light, and in the meantime, you can solve the question like this only. Okay. The only thing is, you will not be able to see my face. Otherwise, everything will be okay. Okay. This light is very heavy. Light consumes roughly 1 kilowatt. For a 1D steady isentropic flow of a perfect gas, which of the statements are true? Total temperature remain constant throughout the flow. Static temperature decreases as Mach number increases. Total pressure remains, again this is MSQ, not MCQ. This is MSQ. Total pressure remain constant across a shock wave. Okay. Entropy remains constant throughout the flow. Okay, I have reframed the question a bit. So total temperature remains constant throughout the flow. Static temperature decreases as Mach number increases. Total pressure remains constant, and entropy remain constant throughout the flow. Which is the correct answer? भूत लग रहा हूं? अबे भूत लगता ही नहीं हूं मैं. सपनों में आके मैं डराता भी हूं. किसी दिन अगर तुम लोगों ने अगर मेरे को ज्यादा परेशान किया ना, तो सपनों में आके मैं डराऊंगा भी तुमको. ओके. तो पावर आ गई है. तुम लोगों को ज्यादा भूत का सिर देखना नहीं पड़ेगा. So electricity is back after 2.5 hours. Okay. So what is the right answer? So guys, it is saying 1D steady isentropic flow. If the flow is isentropic, that means there is no irreversibilities. ठीक है? No irreversibilities. Okay. And if there are no irreversibilities or no losses, then the first thing, total temperature remain constant throughout the flow. That is correct. You know that T01 will be equal to T02. That's correct statement. Static temperature decreases as Mach number increases. This is also a correct statement. So you know that T01 is equal to T1. 1 plus gamma minus 1 by 2 M1 square or M2 square, whatever you want to write. So this is constant. This is constant. If this is constant, then this temperature and M1 both are inversely proportional. If M1 goes up, this M1 square goes up, this whole goes up, so the temperature has to drop. So T1 drops. So this statement is also correct. Static temperature decreases as Mach number increases. That means as the velocity increases, your kinetic energy will increase. So if kinetic energy is increasing, then the temperature has to drop, which is enthalpy. So enthalpy and kinetic energy both will be inversely proportional. Total pressure remains constant if the flow is isentropic. If the flow is isentropic steady, then total pressure also remains constant. Total pressure also remains constant. If T01 is equal to T02, then P01 divided by P02, which is equal to T01 divided by T02 ki power gamma over gamma minus 1. So if this is constant, this whole quantity will be constant and this will be constant. Understood? So the third statement is also correct. Guys, most of you have made a mistake. Nobody has written C. Total pressure also remain constants. Entropy remain constant throughout the flow. The flow is already given as isentropic. What do you mean by isentropic? Isentropic means there is no entropy change. So the flow is isentropic. That means the fourth statement is also correct. I hope everybody has understood this. Got it? Okay, very good. People are saying I have become Mr. India. My God. Okay, chalo. Let's go. Let's do another question. So a steam power plant operates an ideal Rankine cycle. Steam enters the turbine as superheated steam at 10 megapascal, 500 degrees centigrade, and expands to a condenser pressure of 0.1 megapascal. Use the steam data at 10 megapascal. H1 is this, S1 is this. At 0.1, HF, HG, SF, HG is given. The thermal efficiency of cycle is. You have to quickly calculate what is the thermal efficiency of cycle. All the options are given. So quickly calculate what is the thermal efficiency of cycle. This question is going to take you some time. So you have to solve it properly. Tony Stark, 38%. Ah, very good. I hope you are not forgetting. I hope you are not forgetting the pump work. Ah, very good. Is it coming out to be 38%? What is the dryness fraction you are getting? Those of you who have got the answer, what is the dryness fraction you are getting? Hmm? Okay, that's correct. So let's solve this. So the question says there is a Rankine cycle, and if we draw it on TS diagram, then the question is somewhat like this. Location 1, 2, 3 and 4. Okay, so it is given that S3 is equal to 6 point, or at H1 is given. So the nomenclature is different. So nomenclature, what is given is, this is 1, 2, 3, 4. Okay. So S1 is given as 6.5. Okay, 6.5. So we know that process 1 to 2 is isentropic. So S2 will also be equal to 6.5. So S2 will be equal to SF plus X times Sg minus SF. So from here you can calculate dryness fraction X, that is S2 minus SF divided by Sg minus SF. So 6.5 minus 0.65 divided by 7.36 minus 0.65. I hope data is correct. 6.5 and 0.65 and 7.36. Okay. So from here you will get dryness fraction is equal to 0.871. And once you have got dryness fraction 0.871, now you can calculate H2. So H2 will be equal to HF plus X times HFG. So he has directly given you HFG. HFG is 2392. Okay. So from here you can calculate H2, that is 191 plus 0.871 into 2392. What is this value? This value was coming out to be 2271. 2271 kilojoule per kg. So you have got the value of H2. So from here you can calculate work of turbine. Work of turbine is 3410 minus 2279. Okay. So 71, sorry. 3410 is given as the enthalpy H1. Okay. So 2271 and 3410. So this will be equal to how much it was? 1139 kilojoule per kg. Okay. So this is what is the work of turbine. Then you have to calculate work of pump. Work of pump is not given to you. So you have to calculate V into P2 minus, or P4 minus P3. Okay, that is 0.001 into 10 megapascal, 10 into 10 raised to power 6 minus 0.1 into 10 raised to power 6. Okay, so if it is 10 megapascal, you will directly see that it will come out to be 10 kilojoule. In fact, it will come out to be 9.9 kilojoule. So that you can write roughly 10 kilojoule. Okay. So the W net of the cycle will be equal to 1139 minus 10. That is 1129 kilojoule per kg. Okay. And you can calculate what is the heat supplied. Heat supplied will be equal to 3410 minus 191 is the enthalpy H3 plus 10. This will be H4. Okay. So from here you will see this will come out to be 201. So 3209 kilojoule per kg. Heat supplied will be this, and efficiency can be written as 1129 divided by 3209. I think this will come out to be 35%. Is it clear? 2273, 2274. It's okay on the amount of this approximation. So whatever we take over here, Because of that, this will slightly vary by 2-3 kilowatt. Okay, so the right answer is 0.35. Most of you had got it correct, but few of you have got 38. Somebody has written 40. I don't know why or what the mistake that you made. ठीक है? Chalo. So let's go ahead and let's do one more question. So this question is also on regeneration. A modified Ericsson cycle operates without regeneration. So there is a Ericsson cycle which operates without regeneration, uses air as the working fluid. The cycle consists of 2 isothermal process and 2 constant pressure process. The cycle operates between minimum temperature, maximum temperature and pressure ratio 5. No heat regeneration occur between the constant pressure process. The thermal efficiency of cycle is. You have to calculate the thermal efficiency of cycle. Quickly calculate it. This is a very good question. Sir, where is V? V is not given, but for liquid water, you know that V is 0.001. I don't have to give you the V values. Okay. Solve it quickly. This is a very good question. (27) 27%, 36%. Very good. You guys are not solving it properly, man. This is very good question. One of the best questions. Okay. In the meantime, let me draw the cycle. You guys can continue doing the question. Okay. So how do we solve this question? देखो बच्चों, see if it is not given that regeneration is there. If the question was of regeneration, then this would have been very easy question. Okay, because efficiency would be equal to the Carnot efficiency. But it is given that it is a modified cycle. It is not what a simple Ericsson cycle looks like. ठीक है? So this is a pressure equal to constant, pressure equal to constant, pressure equal to constant. So now when you have to calculate the efficiency of cycle will be W net divided by the heat supply. Okay. Now what will be W net? So if you see over here, which all processes will have W net? Okay. So if you see here, all the 4 processes will have W net. There will be heat supplied over here. There will be work out. Okay. So if you supply heat, there will be work out W12. There will be work in W34. There will be work in W41. Okay. And there will be W23. So all the 4 processes will have work. So now you have to calculate all the 4 works and all the 4 heat. But that will become very cumbersome. So you have to apply slightly your mind. So can I say, if the regeneration was given, if in this cycle regeneration was given, can I say W net of the Ericsson cycle, W net will be equal to heat supply 23 minus heat supply 341, WS23 minus Q rejection 41. If regeneration was given, can we say the W net would be equal to the net heat supplied, and net heat supplied is QS23 minus QR41. Can I write it like this? I hope everybody understands this. Okay. So since you have removed the regeneration, that means you have not changed anything on the work. You have removed the regeneration only, so the work remains same. So W net of the cycle will be equal to, W net of the cycle is QS23. QS23 will be temperature higher into S3 minus S2 minus temperature lower S4 minus S1. So you have to calculate S3 minus S2 and S4 minus S1. Now first we will calculate S3 minus S2. Let's say these are the 2 that we need to calculate. So it is given that the pressure is constant over here, pressure is constant over here. So you see, when you are supplying heat, work is getting out. That means expansion is happening. So this is higher pressure, which is 5 bar. And this is lower pressure, which is 1 bar. Okay. So now you have to calculate entropy change. So delta S, S3 minus S2 is equal to Cp ln T2 by T1 minus R ln P2 by P1. Okay. Now temperature is remaining constant over here, so the temperature is constant. That means this first term will go away. You will be left with minus RLN P2 by P1, that is equal to 287 into ln 1 divided by 5 with a minus sign, and from here you can calculate delta S. What will be delta S for this? So the delta S will be equal to 287 into ln 1 divided by 5. So 461.9. 461.9 joules per kg Kelvin. Okay, this is delta S. Okay, so from here you can calculate what is the heat supplied. So W net will be equal to heat supplied. The higher temperature is 900 Kelvin. So it will be 900 multiplied by 461 minus 300 multiplied by 461. We know that both the entropy change will be same. S3 minus S2 and S4 minus S1 both will be same. So the W net of the cycle would be this, that is 600 multiplied by 461. Okay, so that is 277.1 kilojoule per kg of air. Is it clear? So the W net for the cycle is, W net is 277 kilojoule per kg. Okay. Now you have to calculate what is the heat supplied. Okay. So the heat supplied, in case of heat supply QS total will be equal to heat supplied 1, 2 plus heat supplied 2, 3. Heat supplied 1, 2 will be equal to Cp into T2 minus T1. And heat supplied 2, 3 we have already calculated, that is 900 into 461. Okay. So this you can write 1005 into 900 minus 300 is 600 plus 900 multiplied by 461. How much it is coming? So 1005 into 600, 603 plus 900 into 461, 900 into 461, 414.9. That is equal to 1014.9 kilojoule per kg. Okay, so you have supplied 1014 and the work that you got is 277. So from here you can calculate efficiency, that is 277 divided by 1014.9. Okay, so 277 divided by 1014.9. So 0.27. I hope everybody got the answer. Is it correct? Have all of you understood? Most of you have. Only Tony Starr gave the right answer, that is 27. I'm not sure whether he was right or by mistake he got this answer, but that is the only answer that we got. Is it clear to everyone? Yes, I hope you understood this. Are Baba, this is very good question. This is very conceptual question. Is it clear? Okay, chalo. Now let's go to another question. So we have, quickly guys, we have 5 more questions to solve. We have 5 more questions to solve. Let's go to the next question. It says steam expands through a turbine from 10 megapascal 500 degrees centigrade to 0.1 megapascal. The isentropic efficiency of turbine is 85%. The condenser receives the exhaust steam at so and so, so and so. The heat rejected per kg of steam. So this question we have already calculated. समझ नहीं आया? क्या समझ नहीं आया बताओ? What have you not understood? Tell me what have you not, what you guys did not understand in this question. Have all of you understood? Okay, I just want to see thumbs up, those of you who have understood. Sir, this W net formula by TDS equation. Okay. So let me draw the Ericsson cycle, modified Ericsson cycle once again. Okay. So let's see. This is your cycle. ठीक है, TS. Okay, so location 1, location 2, 3 and 4. Okay, this process 1 to 2 is a constant pressure process. Pressure equal to constant and pressure equal to constant. This is your 300 Kelvin and this is your 900 Kelvin. Okay, so let's go to process 1 to 2. Let's go to process 1 to 2. I hope everybody will understand this. This process is happening at a constant pressure. So what is the heat supplied? What is the heat supplied? Can I say for 1 kg of air, m dot into Cp into T2 minus T1, can I write it like this? So 1 into 1005 into 900 minus 900 minus 300. So this is the heat supplied. Can everybody understand that if I take this to be, let's say 1.00. So this will be 600 kilojoule per kg. I hope everybody can understand this. See, the problem that is with you guys is you do not understand the basic concepts. That is what is the problem. This is the one question which is different from, or this is the one question which is purely based on the concepts. So heat supplied will be 600 kilojoule per kg. Out of this 600 kilojoule, how much is the work developed and how much is the energy which is going into the internal energy? So you know that delta Q is equal to delta U plus delta W. And what is delta Q? You have already written 600. What is delta U? Delta U will be CV delta T. And remaining will be delta work. So from here, that is W12 can be written as 600 minus 0.718 into 600. Can I write it like this? So the work that you will get is, W12, it will be equal to, let me calculate, okay. So 600 minus 0.718 into 600. So 169.2 kilojoule per kg. This will be the work that you will be getting out. So you are supplying heat from here. You are supplying heat 600 kilojoule per kg. And you will be getting W12 out. That is equal to 169.2. What is the change in internal energy while going from here to here? The change in internal energy will be 600 minus 169. That is 430. Okay. So this you have understood. Everybody has understood. Okay. Now let's come to this. 3 to 4. 3 to 4 is again a constant pressure process. Here the heat is getting rejected. Here the heat is getting rejected. How much heat is getting rejected? Again mCp delta T. You will see the heat getting rejected will come out to be 600 kilojoule per kg. Okay. Heat getting rejected will be 600 kilojoule per kg. Okay. There is a change in internal energy over here. Okay. What will be the change in internal energy? So, hold on a second. Did we make any mistake? mCv delta T 600. Okay. So, for 3-4, process 3 to 4. Process 3 to 4. So you have heat rejected will be mCp into delta T. That is equal to 1 into 1000 into 600. That is 600 kilojoule. So 600 kilojoule per kg is getting rejected. So from here to here. Okay. That's correct. So from here 900 to 300 you are coming out. So you are rejecting 600 kilojoule per kg. Okay. Now this delta Q will be equal to delta U plus delta W. Okay. So delta Q will be equal to delta U plus delta W. So 600 is going out. That means this is minus 600. That will be equal to delta U. Here the internal energy is also changing and that is reducing. So it will be minus, or it will be CV into 300 minus 900, okay, plus delta W. So from here you will see that the delta W that will come out to be, it will come out to be minus 169.2 kilojoule per kg. Again it will come out to be same, minus 169.2. This is minus 600, this will come out to be minus 430, and this remaining will be minus 169. Okay, so that means you have to provide a work inside to this cycle which will be equal to 169.2 kilojoule per kg. Okay, so that means if you see this cycle, there will be 600 coming out and you have to provide work input of 169.2 W34. So if you see both these processes, they are just replica of one another. That means whatever is the energy you are supplying here, the same energy will come out. Whatever is the work that you are supplying here, the same work will come out. So now if I want to write what is the W net of cycle, you see that whatever is the work that you are providing over here is coming out over here. So both these work will cancel out. One is positive, other is negative. So they will cancel out. So the only work that is remaining is the work which is coming out from here, W23, and the work that you are providing here, W41. So the net sum will be W23 minus W41, and this will be equal to the heat supplied over here, Q23 and Q41. Since the processes are isothermal, if the process is isothermal, heat and work will be exchanged. Whatever is the heat you are supplying, the same would go in the work out. Whatever is the heat which is coming out, the same has to be supplied in work. So W net will be equal to Q net, that is Q23 minus Q41. And that is what I had written over here. W net is equal to QS23 minus QR41. I hope now everybody understood. Have all of you understood this? I am sure now it is clear to everyone. Yes, it should be. Okay, chalo, let's go ahead. Okay, so let's solve this question, the Rankine cycle question, where you have already seen what is the isentropic efficiency. Sorry, H2S. How much it was? 2279 kilojoule per kg. I hope everybody remembers. Okay, so solve it. विदाउट रीजनरेशन है तो सप्लाइड हीट में Q12 भी ऐड हो जाएगा, तो हमने ऐड तो किया ही है भाई, कुशाग्र हमने ऐड तो किया ही है. ओके So what is the right answer? So guys, we had already calculated H2S. So you see, while drawing the Rankine cycle, in the question we had already seen that the process was from here to here, it was isentropic. Okay. Now it is saying that the process is not isentropic anymore. It is moving with irreversibility. So, and the efficiency is 0.85. So this is 2s and this is 2, this is 1, and this is location 3. Now he is asking what is the heat rejected in condenser. So heat rejected in condenser would be equal to H2 minus H3. Okay, H3 is already given as 191 kilojoule per kg. So we have to calculate H2. So to calculate H2, we have to use isentropic efficiency of turbine, that is H1 minus H2 divided by H1 minus H2S. So from here you can calculate H1 minus H2, that is 0.85 into 3410 minus 2279. Okay. So from here you will get H1 minus H2, and this was coming, I think, 961. So it was coming out to be 961.35 kilojoule per kg. And once H1 minus H2 is calculated, you can calculate H2. H2 will be equal to 3410 minus 961.35. That will be equal to 2448.65. 2448.65 kilojoule per kg. So now you have got H2. So from here you can calculate heat rejection. Heat rejection will be equal to 2448.65 minus 191. So this will come out to be 2257 kilojoule per kg. Most of you got the right answer. Very good. Okay. But I hope you understood what is the isentropic efficiency of a turbine. H1 minus H2 divided by H1 minus H2S. Is it clear? Chalo. Let's do one more question. So this question is on open feed water heaters. So in a Rankine cycle, some steam is bled from the turbine at 2 megapascal to heat feed water in an open feed water heater. Mass flow of turbine steam 15 kg, enthalpy of bleed steam 2800, enthalpy of feed water 200, enthalpy of water leaving 800. Find the fraction of steam bled. You have to calculate how much is the steam which has been bled. Okay. So quickly calculate. 'What is the mass fraction that has been bled? .23. Okay, very good. So question क्या कह रहा है? Question is saying that there is a feed water heater. In this feed water heater, there is a steam coming with an enthalpy of 2800, and let's say the fraction which is bled is y. Remaining the fraction 1 minus y will be coming in as a feed water with an enthalpy 200, and when it is going out, it is going out 1 kg with an enthalpy of 800. Okay, so you can do the energy balance on the feed water, that is y multiplied by 2800 plus 1 minus y multiplied by 200 will be equal to 800. And now you can solve this. Y will come out to be 0.2307. Oh, somebody has also calculated the efficiency. Efficiency is equal to 35%. Very good. Hmm? But tell me, how did you calculate the efficiency when there was nothing given about what is the enthalpy at exit of boiler? Hmm? When there was nothing given about the enthalpy at exit of boiler, how could you calculate? So now the question is given, steam power plant operate on Rankine cycle. Steam enters the turbine as superheated steam. Some steam is bled at 2 megapascal to heat the feed water. Mass flow rate of steam entering turbine 15. Enthalpy of turbine inlet 3410. Enthalpy of turbine exit at condenser 2276. Enthalpy of bleed steam 2800. So and so, so and so, so and so. The turbine work output will be in kilowatt. So now calculate what will be the turbine work output, and now if you want to calculate, you can calculate efficiency. Okay, so quickly all of you solve it. What will be the turbine output? Quickly calculate. What is the power output? Array, is it so difficult question? Eh? This is very easy question. Why is it taking so much of time? Fifteen 196 kilowatt. Wow, very good. Very good, very good. Anybody getting 966, 9600 also, or 18,000? Oh, 3924. Very good. We have got multiple answers. So, guys, it is saying that there is a turbine. In that turbine, there is 15 kg of steam is coming out per second, and it is coming in with an enthalpy 3410. And at certain location where the enthalpy is 2800, 0.2307 multiplied by 15 times of the steam is taken out and remaining is going out, and it expands to 2276. So what is the work of turbine? So work of turbine will be equal to 15 kg expands from 3410 to 2800. This is the complete steam expanding from here to here. So 15 into 3410 plus 2800 plus. Now 23% is taken out and remaining is going out. So 1 minus 0.2307 multiplied by 15. So much of the steam is remaining, and that is expanding from 2800 to 2276 kilowatt. So this is what is work of turbine, and it will come out to be 1.15156 kilowatt. Okay. So most of you have done it correct. I hope everybody understood what is this. Okay. This is the amount of steam which is going further. So steam which is expanding till condenser. Okay. Chalo. Let's go to the second last question. Second last question of the day. Air flows isentropically through a convergent-divergent nozzle. At a certain section of the nozzle, the static pressure is measured as 120 kPa, while the stagnation pressure at the inlet is 300 kPa. Assume air to be perfect gas with gamma equal to, why he has written G? Gamma equal to 1.4. The Mach number at that section will be. Please repeat. What should I repeat? Arey, what is there to repeat in this, yaar? What is there to repeat? I don't know what you want me to repeat. Chalo. Those of you who have understood it, solve this question. Quickly calculate the Mach number at the location where the static pressure is 120 kPa. Second part. What second part? 1 minus 0.2307. Acha, you calculate it on 1 kg. If there is 1 kg steam that is coming in, how much will be the power developed? You calculate it on 1 kg steam that is coming in. Array, 23% of the steam is extracted. So if 23% is extracted, remaining 77% is going, no. So 77% multiplied by 15, that is the mass of steam that is going. What is the Mach number? 1.2. Okay. Very good. 1.27 is wrong. 1.27 is wrong. So it is saying that at certain location, which is at location 2. So P2 is given as 120 kPa, and he is saying that at inlet P01, P01 is 300 kPa. So we have already discussed that if the flow is moving isentropic, then the pressure remains constant. If the pressure remains, total pressure remains constant, that means P01 will also be equal to P02. So from here you can calculate that P02 is 300 kPa, and from this P02 you can calculate T02. So T02 divided by T2 will be equal to P02 divided by P2 की power gamma minus 1 over gamma. Okay, so T02 divided by T2, this you can write P02 is 300 divided by 120, इसकी power 0.4 divided by 1.4. So when you will solve this, you will get T02 divided by T2. This will be equal to 1.3. Okay, and we know that at any location, the relation between temperatures can be written as 1 plus gamma minus 1 by 2 into M2 square. Okay, so T02 by T2 is 1 plus gamma minus 1 by 2 into M2 square. Is it clear? So from here you can calculate M2. So M2 will come out to be square root of 1.5. That is 1.22. Okay, so the right answer is 1.22. Is it clear? I hope everybody understood this. Huh? Very good. If you have understood, then let's go to the last question of the day. A convergent-divergent nozzle is designed for an exit Mach number of 2.2. If the back pressure is gradually increased from the designed value, I think it should be MSQ. If the back pressure is gradually increased from the design value, the first event to occur inside the nozzle is reduction in the throat Mach number, formation of normal shock in diverging section, flow becoming, okay, so this will be MCQ. Choking is lost immediately. Okay. So convergent-divergent nozzle is designed for an exit Mach number of 2.2 if the back pressure is gradually increased from the design value. Gradually means slowly, slowly. So what will be the first thing that you will observe? Reduction in throat Mach number, formation of a normal shock in the diverging section, flow becoming subsonic everywhere, and choking is lost immediately. That means flow does not become the choked flow. Compressible flow पढ़ा ही नहीं. Very good. Flow becoming subsonic everywhere. So this is a convergent-divergent nozzle. So let's say over here Mach number 1 is 0. At throat the Mach number will be equal to 1, and over here the Mach number M2 will be equal to 2.2. Corresponding to that, there will be certain pressure exit which will be over here, which is design. Now as you increase the pressure over here, so what happens is, whatever is the fluid that was supposed to go out, now you are restricting that fluid motion. You are not allowing that fluid to pass freely. So what happens is, the moment you resist the flow over here, when you resist the flow over here, you will see that these particles which are coming at very high speed, they will collide. And when they will collide, they will have reduction in velocity. That means kinetic energy will get converted into the enthalpy or pressure energy. So there is a sudden pressure change. Now, the moment you start increasing this pressure at this interface, when the flow starts becoming or reducing in the velocity over here, the particles which are over here, they will start experiencing the stop, sudden stop. Okay, and you will see that the first thing that you will observe is there will be a shock wave which will be formed just upstream of the exit. This is the exit. Here the pressure you have increased. So when you have increased the pressure at just the exit, you will see that there will be a shock formed. So the first thing that you see is formation of a normal shock in the diverging section over here. As you continue increasing the flow, that means you restrict the motion over here, this shock will start moving upward, 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 upward. And in extreme conditions, this will reach over this location. It can never reach the throat. Okay? Until and unless the flow has, or I should not say never, it will reach the throat when the design pressure becomes almost equal to, there is something called as the sonic pressure. So there is a design pressure over here where this section will become as a nozzle and this will act as a diffuser. Okay, so the pressure, there will be a certain pressure over here where just the Mach number is becoming sonic over here. So till that time, the shock will reach over here, and once you have removed that, once the flow has become sonic, the shock will disappear. Okay, and after that, the flow will become not sonic over here. So that condition would be coming in the last. Okay, so the choking, this will come in the last, flow becoming subsonic, this will become in the last, reduction in throat Mach number. All the three phenomena will happen together. But this is the first phenomena that will happen. So shock will move, start moving from here, 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 here. It will continue and it will reach at the throat, and after reaching the throat, it will disappear. Okay, so the first thing that you see is the formation of a normal shock wave. I hope everybody has understood. Yes or no? So if all of you have understood, then guys, we have come to end of today's class. I hope everybody must have enjoyed the questions that we have done over here. Did you enjoy the questions? The level of questions was good. These are the type of questions which I feel you will see in the exam. Somewhere related to these questions, you will see the questions in exam. Okay, so with this, let's stop it over here. Okay, thank you so much. Okay, and we have one more session today, that is at 7 o'clock, and that is on GATE Wallah ME. There also we will discuss few more questions. Okay, thank you.